Professor Nilo, Technology and Engineering. Today's session, we are going to discuss a topic called internal expanding shoe. This particular topic, we talk about internal expanding shoe brick and its mechanism with its design. So now let's move on to what exactly internal expanding shoe brick is. Internal expanding shoe brick is a type of brake which provides a braking torque with the help of creating a pressure on rotating element and by creating a friction force to stop that rotation. So in this particular session, we will going to discuss about how this mechanism will going to work and how the step-by-step design, or you can say a movement, or you can say a particular component will going to design by. So let's move on to that. So here you can see an schematic diagram for an internal expanding shoe. Here, first of all, here it is internal expanding shoe brick consists of shoe S1 and S2 which is pivoted at point O1 and O2, which is having a mounted brake liner material and a spring which is connected through a cam to actuate that two particular S1 and S2. Okay? I hope you got this arrangement very well. The outer drum is an rotating element which is rotating right now in anti-clockwise direction. So S1 and S2, after pressurizing them, they will create pressure on wall of this rotating. Let's get into this mechanical, or you can say free body diagram of internal expanding shoe brake and try to understand how this force is going to perform. Okay? So after applying force F1 and F2, they both will create two types of force on our internal expanding shoe brake. One will be a reaction force, or you can say a reactionary force, exactly opposite direction to this F1 and F2 from this shoe, and they are acting through this O1 or an O2 with pivoted point. At the same time, to oppose that rotating movement, the frictional force will be created on this particular rotating element. Clear? In the case of S1, it will going to be downward side, and in the case of S2, it will going to upward. Let's talk about what type of output will going to, or resultant moment will going to produce due to F1, Rn and Df. F1 will try to push R to S1 2.01, clear, with the length L. Clear? So ultimately it will try to create an anti-clockwise movement. At the same time, RM will try to create clockwise movement in inside with 2.0 B. Here you can see that point B, clear. OA is our radius having R, the one element we have considered. We will talk about that later. At the same time, this frictional force also will create anti-clockwise moment. So here you have got this point that F1 and DF will be anti-clockwise, Rn will be clockwise. At the same time on S2, Rn will be anti-clockwise, DF will be anti-clockwise, and F2 will be clockwise. So here this F1 and friction force will be supporting each other. Here F2 will be opposing, all the movement will be created by S2. Now let's talk about the consideration we have going to design on, based on which design we will going to have. Here you can see theta 1 and theta 2 angle made by material, brake liner material, top of my brake liner material with O1 and bottom of brake liner material with O1. The top angle will be called as theta 2, bottom angle will be called as a theta 1. Now let's consider a smaller element which is Ca on this particular brake liner material, and after applying force this Ca will be moving. Now we will consider this action on the Ca, and then we will try to find how this action will directly affect our design or movement of this particular internal expanding shoe. So let's consider this. The internal expanding shoe brake is having a radius R, which has width B, which has maximum pressure P1, normal pressure Pn, and F1, F2 force acting upon that. Here O1B is O1 sine theta. So here the distance of that particular force Rn from that O1B is denoted by, in terms of O1, which is O1 sine theta, because I have to convert and I want to convert each and every terminology in terms of sine theta as well as O1 and R, because those are the reference points and reference nomenclature which we are going to use while designing. Clear? This particular normal force is related to direct force or maximum force, even sine theta, and which is creating a normal pressure into the area of particular element. Now let's find out the force. There are two forces which we have talked about. One is the normal force and another is frictional force. And both these forces will try to create that frictional torque, or you can say. Let's talk about first of all that particular reaction force acting on that smaller element which we have considered AC, which is having area of BR d theta, where B is its width and R d theta its radius into its angle, which is representing its arc. So ultimately, the pressure or force generated by that particular element is called PN, RN. It is PN into area, which is P1 sine theta BR d. Now let's convert that into frictional force. This frictional force is nothing but multiplication of coefficient of friction with this normal force, and which is represented by mu into P1 sine theta into BR d theta. Now ultimately this frictional force will help us to create a frictional torque, which is d theta, dt, and this dt is nothing but the multiplication of this frictional force into radius. Here, so it will be df into r, and ultimately it will be mu p1 sine b r square d theta. I hope you got this point. To find out total torque acting upon this element, or a braking torque acting upon this particular element, we have to integrate it from theta 1 to theta 2, where theta 1 is bottom portion or bottom limit of our gliding material and theta 2 is top portion of our lining material. So ultimately here we have provided integration of this particular dt, which is represented by mu p1 pr square theta 2 to theta 1 sine theta into mu is which is equals to, we have provided this in sine theta is minus cos theta, and ultimately it will be represented by mu p1 pr square cos theta 1 minus cos theta. Yeah. So moment of force, this, now we have to find moment generated by this reaction force as well as frictional force. Now moment generated by reaction force, or you can say Mn, or a normal force, which is acting through O1, which is represented by delta Rn into its longitudinal distance or perpendicular distance, which is drn o1 sine theta, and ultimately it will be p sine theta br d theta o1 sine theta. So we have to integrate this from theta 2 to theta 1, which is our term is p1 sine square theta br theta d theta o1. So let's move on to that particular integration. Now let's have our integration to find total moment generated by this particular element, which is Mn. Here from theta 1 to theta 2, P1 sine square theta, Pr theta d theta over. Now if I want to integrate this sine square theta d theta, I have to convert that into terms which can be integratable, which is sine square theta is equal to 1 by 2. Ultimately, my final equation will be look like it's 1 by 2 p1 br over theta minus sine 2 theta by 2. Let's put the limit inside this. So ultimately, after putting limit inside this, it will look like this: 1 upon p1 br over theta 2 2 minus 1 by 2 sine 2 theta minus sine 2 theta 2. This is moment generated by r frictional, sorry, are normal force, normal reaction. Now let's talk about moment generated by frictional force, which is acting through perpendicular distance AB at point O1, and which is represented by dF into AB. So dF into AB will be nothing but R minus O1 cos theta. Because from our diagram, you can see from this diagram, this particular B point and this is particular A point. So this is, AB is nothing but total R minus OB. Clear? So that particular relation we have used here, R minus OB, which is O over. Now we are converting that OB into O over cos theta by considering this smaller triangle, which is O1B. Clear? So O1 cos theta, and then we will put integration for the to find out this particular element. Now let's simplify this particular equation. Let's multiply this sine theta inside this particular value. So ultimately we will find mu p1 br into r sine theta minus 001 by 2 sine 2 theta d theta. Now let's have integration of this particular element from theta 1 to theta 2. After applying integration, we find out this particular equation. This is final equation. Is mu p1 br r into cos theta 1 minus cos theta 2 theta over by 4 cos theta 2 minus cos theta 1. Clear? These are two moments generated by our normal reaction as well as frictional force. This normal reaction and frictional force will decide what type of force and what amount of force we have to put on our shoes and what kind of reaction it will be generated due to that. Now let's talk about the reaction generated at shoe oven. Clear? Then that point F1 into L is equals to moment generated due to normal reaction minus moment due to friction, because both are creating reaction in opposite direction. That normal one in clockwise and one anti-clockwise. But in the case of shoe as to both the reaction normal as well as friction or moment generated by both of them are supporting each other. So ultimately it will be summation. So in the case of 2s1, if frictional moment is increased compared to normal moment, then your shoe will get into or your brake will get into self-locking phenomenon. So to avoid this self-locking phenomenon, we have to make sure that the frictional moment should be always lesser compared to our normal reaction. I hope you got this each and every terminology in this particular derivation. This contains 7 marks even as well as our examination. I hope you got this point very well. I have taken this particular theory directly from machine design by R.S. Kurmi. Here, I hope you enjoyed the session. If you are having any doubt regarding to this session, you can directly ask me, contact me.